Hello, fellow researchers. Welcome to this presentation on the topic of comfort and time efficiency in motion planning, a roundabout case study. This work is presented at ITSC 2021 for the special session of revisiting the design of automated vehicles for enhancing motion comfort. My name is Zheng, and this work is done in collaboration with Dr. Shyrokau and Professor Keviczky. We all work at Delft University of Technology at this moment. So why we found this topic important? Apparently, some of the key societal benefits of automated driving depend on comfort. It allows people to effectively utilize the travel time that was spent on driving before, and it provides mobility for individuals with special needs, like those with high sensitivity to motion sickness. And it's fair to say that motion planning is majorly responsible for the comfort aspects of automated vehicles. There are a large number of existing studies that work in this direction to make motion planning more comfortable. There are heuristic approaches that ensures the smoothness of the planned motion, and there are optimization-based approaches that minimize certain criteria like jerk or acceleration. And some of these studies actually included another very important factor in motion planning, that is the time efficiency. Still, we've found something missing in the existing studies. One of them is that each of the studies needed to develop its own testing scenario, and each scenario is actually not fully representative of normal daily driving. Additionally, there is no agreed quantitative measure to evaluate the performance of a motion planner, especially in terms of comfort. And with these two components missing, it is then not possible to fairly compare motion planners to human drivers in order to demonstrate the superiority of automated vehicles. So in our study, we aim to bring this gap a little bit closer by comparing how human drivers and motion planners perform at roundabouts. To observe the human drivers, we analyzed first the naturalistic driving data that's given in the so-called ACFR5 roundabouts dataset. It contains a large number of recordings at public roundabouts and recorded vehicle trajectories with LiDAR sensors. Of course, it suffers from certain drawbacks that are the measurement errors and sensor noise. To overcome these issues, we came up with our optimization-based motion reconstruction method. It basically incorporates the point mass kinematics and minimizes the cost function to penalize the deviation from the original measurement, as well as the maneuvering effort needed to follow certain trajectory. On the right-hand side, we have an example of how our method performs. So the gray circles here are the original measured coordinates of the vehicle. It is apparent that the measurement is very noisy. And the blue line here is the baseline reconstructing method with polynomial fitting, and the red line is using our method. At the first glance, it seems that the two methods generate very similar results, but if we look deeper at the velocity and acceleration profile, it is very obvious that our method is able to generate more reasonable and realistic motion profiles than polynomial fitting. And after reconstructing all the recordings in the dataset, we further performed a so-called DB scan algorithm in order to remove the outliers. Here we show a collection of reconstructed paths at one of the recording locations. Two observations actually stand out if we look at this figure carefully. One of them being that the road has a wide median area in this left to right direction. It is designed in this way to allow vehicles to pass more easily without having to slow down as significantly as the vehicles passing in the other directions. And another point is that the recordings are, in a sense, not complete. The vehicles are only detected shortly before they enter the intersection, and the recording stops immediately after they leave the roundabout. This is mainly because the authors of the original study were more interested in how vehicles behave inside a roundabout, while we are trying to look at it from a different angle. And these two observations indeed have an impact on the distribution of peak accelerations that we observed from human drivers. The optimized road geometry allowed vehicles passing straight at the roundabout to exhibit a significantly lower lateral acceleration compared to the other vehicles. And the incomplete recordings caused the human drivers to exhibit a much lower peak longitudinal acceleration than what is considered as practical. Then moving on to the second component of our study, the optimal motion planning at roundabouts. Here the objective is to minimize the weighted sum of discomfort and travel time. That is essentially to deal with the trade-off between comfort and time efficiency. To measure discomfort, we use the integral of squared planar acceleration over time, and then we place the weighting factor W on the travel time. It's varied between 0 and 4 with an interval of 0.5. By assigning 0 to W, we are actually obtaining the comfort optimal motion. And because the duration of the maneuver would change in the optimization process, we had to define the motion in space instead of in the time domain, as more often done before. So on this page, we present the comfort optimal motion profiles at a roundabout. We observed that the vehicle should always preposition itself to the left-hand side of the lane in order to minimize the curvature. And when turning right, the vehicle would not always follow the lane center of the roundabout, but instead it simplifies 3 consecutive bends into 1. In the other 2 cases, the vehicle would stay as closely to the center island as possible in order to allow more space for the transitioning phases of the maneuver. Another interesting observation, although not directly seen on this figure, is that when we change the value of W from 0 to 4, the spatial path of the vehicle actually does not change as much. Instead, it's the velocity profile that plays a bigger role in changing the balance between comfort and time efficiency. And on this page, we further explain how the value of W would impact the planned motion. On the left-hand side, we see how W influences the time efficiency and comfort of the planned motion. On the lower right-hand corner, we have W equal to 0. That's when we have the longest duration of the maneuver, but also the best comfort. And with a reasonably small W, we are able to achieve a good balance between comfort and time efficiency, but further increasing W would cause comfort to deteriorate very quickly, while the benefit on time efficiency is limited. And on the right-hand side, we show the variation of peak acceleration observed through the maneuver of the optimal planners, and is compared to the values observed from human drivers. And for the reasons explained before, the human drivers show here a much lower peak longitudinal acceleration, and for the vehicles passing straight through a roundabout, they also show a smaller peak lateral acceleration as well. But for the other situations, we observe a matching of peak lateral acceleration when W falls between 1 and 2. And this is actually the same range when we consider the balance between time efficiency and comfort is good. To conclude, our work has gained interesting insights into how human drivers approach a roundabout that's a fairly complex driving scenario, and we have performed a separate numerical study to show how optimal motion planners can handle a roundabout while keeping in mind the trade-off between comfort and time efficiency. Lastly, we've made a brief attempt to make optimal motion planners resemble human drivers in the sense of a matched peak lateral acceleration. Of course, there are certain drawbacks in our study that we aim to improve further in the future. First of all, the source of naturalistic driving data is not completely satisfactory. There are problems with it that prevent us from further comparing human drivers and motion planners. And of course, the roundabout is only a small part of daily driving. We are still on the way to developing this comprehensive testing scenario for all motion planners. And our choice of measuring comfort with the integral of squared planar acceleration over time can be considered a bit arbitrary. And we are trying to validate this choice by experimental studies where we are going to observe the correlation between this quantitative measure and the subjective feeling of the passengers. Last but not least, we are also developing here at TU Delft an active suspension controller for automated vehicles, and we are very interested in seeing whether combining motion planning with active suspension control would contribute to the further improvement of comfort of automated vehicles. And this brings an end to the presentation. Thank you very much for your attention.